Welcome to this session. In this session, we introduce the chapter on numerical methods of solving nonlinear equations. Nonlinear equation that will be solving the algebraic and transcendental equations. And before we start discussing the nitty-gritties of the chapter, there are key things that you require to be able to solve problems in this chapter. So the first and more foremost, you require a calculator. And the recommended calculator is the version of FX 991 ES Plus. And then you require a pen, and you require a bunch of papers for doing the calculations. So let's give the introduction of the chapter. So as I've said, the topic is numerical methods of solving algebraic and transcendental equations. So the objective of the chapter, we are going to be solving equations of the form f of x equals to 0, f of x equals to 0, where f of x is either algebraic or a transcendental function. Now, an algebraic function f of x is a function that is made up of either polynomial or a division of polynomials, while a transcendental function is a function that has trigonometric parts, exponential parts, logarithmic parts, or trigonometric terms in the function. So for instance, if I have f of x given by x power 3 plus 4x plus 3, so this is an example of an algebraic function. So this algebraic function, now when we write x cubed plus 4x plus 3 equals to 0, then it becomes an algebraic equation. So this now will be algebraic equation. Other examples of algebraic equations include x power 4 minus 7x cubed plus 3x plus 5 equals to 0. This is another example of algebraic equation. Or we can have x power 6 plus 4x squared plus x plus 3 equals to 0. This is also an algebraic equation. Now, transcendental equations are equations which have either trigonometric terms, logarithmic terms, exponential terms, or the inverse of the trigonometric functions. So for example, if we have 3 tan of x plus 3x plus 10 equals to 0, this is a transcendental equation because of this trigonometric part. And then if we have x minus 3 sine 2x equals to 0, this is also transcendental equation because of this trigonometric part. If we have x e raised to x plus 4x plus 6 equals to 0, this is also a transcendental equation because of this exponential part. Other examples include if I have ln of x plus x squared plus 3x equals to 0. This is also transcendental because of this logarithmic term. Also, if I have tan inverse of x plus 3x plus 5 equals to 0, this is also a transcendental equation because of the this inverse trigonometric part or trigonometric term. So the objective of this chapter is to solve equation of the form we are going to be solving equations of the form f of x equals to 0, where this f of x is either algebraic or transcendental. Now, one key thing, students make some mistakes when they are solving such kind of equations. Ensure that whenever you are dealing with transcendental equations, mostly where we have the trigonometric or inverse trigonometric part or the hyperbolic functions, your calculator should be in radian mode. So when you are solving this equation, f of x equals to 0, and mostly whenever the f of x has trigonometric term or inverse trigonometric term or product of polynomials and trigonometric or inverse trigonometric or hyperbolic functions, to get the correct answers when you're computing your values for the approximate solution of the equation, ensure that your mode is in radian. If you don't take care of that one, then you may get some erroneous solutions. So we define what we mean by a solution to such an equation. So definition, solution, so algebraically, so there are two ways of defining a solution to the equation f of x equals to 0, either algebraic or geometrical. So algebraically, the real number alpha is a solution to the equation f of x equals to 0 if and only if f of alpha gives 0. That simply means that when you replace x for alpha, then it satisfies the equation. Geometrically, the real number alpha is a solution of the equation f of x equals to 0 if the graph of f of x meets the x-axis at the point x equals to alpha in rectangular coordinate system. So for instance, if this is the graph, y-axis, and then this x-axis, this x 0, and then this is the y-axis. Then if you have a graph this is our an arbitrary function f of x. So y equals to f of x. Then if you say alpha is the solution of the equation f of x equals to 0, then this is the point where we have the alpha, where the graph meets the x-axis. So a solution to the equation f of x equals to 0 is also called the root or 0 of f of x. So root, solution, or 0 actually are synonyms. Now, so we have said that we are going to be solving the equation f of x equals to 0, where f of x is either algebraic or transcendental. And in most cases, this the structure of the function f of x is nonlinear. So the objective so let's call this one equation 1. So the main task is to approximate the value of x which satisfies equation 1. Now, let's state a theorem from real analysis that will help us to be able to carry out this approximation. So if a function, so we state the theorem without proof, a function f of x assumes values of opposite signs at endpoints of the interval a to b. Thus we mean that if we get the value of the function at point A, we multiply by the value of the function at point B, we get a negative number. Then there exists at least one root or solution of the equation f of x equals to 0. So whenever that a function f of x actually a continuous function, f of x assumes values of opposite signs at endpoints of the interval ab. That's to mean that the value of the function at a times the value of the function at b gives a negative value. Then there always exists one root, at least one root of the function or of the equation f of x equals to 0. So we can actually pictorially, this is really what we mean. So this is the y-axis, this is x-axis, and say have another case here, x-axis, and then y-axis. Then we are saying if we have A here and we have B here, so we can have this y equals to f of x. We have A or we have B here, so we can have this y equals to f of x. So you see in these sketches that I've drawn, if so, this is what will give f of A, and then this will be the value of function at B. Now this is f of A, and then when you extend this to the graph, this is f of B. So you see f of B here is on the top of the x-axis, so this is a positive value. This one is below the x-axis, so this is less than 0. This one is on top, so greater than 0. This is less than 0. So you see, because y equals to f of x is a continuous function, then with f of A being negative, f of B being positive, then we are always assured that the graph cuts at least one point on the x-axis between A and B. Similarly, for this case, f of A is negative, f of B is positive. So you see this graph, because f of x is assumed to be continuous, then must at least cut the x-axis at some point. Now, we are going to make some assumptions for us to be able to carry out the approximation of the solution of the equation f of x equals to 0. And these assumptions are the ones that are going to help us to study various methods of getting the solutions of the equation f of x equals to 0. So the first assumption, I will say that f of x is continuous and continuously differentiable up to sufficient number of times. And then assumption number 2, f of x equals to 0 has no multiple, this is very key, no multiple roots in the interval A to B. So we are only going to deal with methods which approximate only a single solution between the interval A and B. So therefore, all the calculations that we are going to do will majorly or will only be approximating one or single solution for the equation f of x equals to 0, not multiple equations. So then the process, before now we list methods of approximation of the solution to the equation f of x equals to 0. So approximately, the isolated roots. Now, when we say isolated root is what we say in the first assumption, that we are only dealing with one solution in the interval A and B of the equation f of x equals to 0 has two stages. So the first stage is isolating roots that is actually isolating roots, that is finding the smallest possible interval AB such that f of A times f of B will give you a negative solution, a negative value. That simply means that the sign of f of A and sign of f of B are opposite. Number two, improving the values of the approximation of the approximate truth to the specified degree of accuracy So that's the second step. So improving the values of the approximate truth to the specified degree of accuracy is now what leads us to now stating the different methods of doing the approximation. So methods of approximating solution of the equation f of x equals to 0. So we are going to discuss 4 methods, and we are going to list the order in which we'll be discussing each of the 4 methods. So the first method is what we call the bisection method. Second method is what we call regular foci. Method, also called method of false position. Number 3, Newton-Raphson method. And lastly, second method. So in the next session, I will start with the discussion of the first method, what we call the bisection method. So let's meet there.